we have these equations, and one of the primes must be 7 because the right hand side has a factor of 7. So let's let p equals to 7, and then we can substitute p equals t into the equation above here, and we can get the equation like this, and divide both sides of the equation by 7. Then we have this one, and rearrange the equation here. Add 1 to both sides to the factors, which can be factored as. Now we can find the prime values of Q and R, since Q and R are primes, and it is equals to 8, so the factor pairs of 8, they are it is like this. And also talk about into different cases. First one, if Q here and R here, then Q equals 2 and R equals to 9. But 9 is not a prime number. In case 2, case 3, but this is not a prime number here. Let me see. Yes, and for case 4. This is not prime, but R equals 2 it is. And then we calculate we have P, Q, and R, or Q, and get them together. That is, so the value of the total. Okay, now let the number we are looking for it be x. We know that x. Okay, from the first one we can write x. This is for the k, and then substitute it in the second one we wrote before, and simplify the left hand side of the equations that we know that. So it is becomes now and also we need to find the m, another letter for m. We can check the values m equals 1, 2, 3, 4. When m equals 2, we know that 3 multiplied 2 equals to 6. And so multiply both sides of the 3k. We can get k. And next, we can substitute the k. and expand the expression here. We have x, another one. And find the smallest positive value of x when n equals 0 and x, we have 37. Okay, and for x equals to 37, we divide it by 13. And when divided by 5, like for here, and the smallest positive number that satisfies the given conditions is 30. We divided this into two parts. For the second one, since it contains at least 3 factors of 5, here, right here, and we can write it here. That is a multiple of 1000. That is equal to 0. And also we talk about the first part for the 20. And calculates the last 3 digits of the difference. So the 100 digits is 0, and the answer is 0. First calculate the pattern of the last 2 digits of powers of 15. The last 2 digits are 15, and when it's square, that is 25. And that is 75. And when we want it to be this number that we know for every n bigger than 2, this one will end with 25. When it is multiplied by the appropriate powers of 3, since this number is even, so the last 2 digits it is 25. And for this one, we know that the last 2 digits are 17. And then we calculate here. That is here. And so the 10th digits, that should be 0. And the answer is 0. Test small prime numbers for each options. We can evaluate each expression for the smallest prime numbers, like p equals 2, 3, 5, 7, 11, to check if the result is ever prime. If we choose the third one first, like for here, we know that So that is not prime. Right, and for p equals to 3, also not prime. For p here, not prime one time. And for p here, also not prime. And this is also not prime. So we know that C is the correct answer here. To determine a possible value of Sn plus 1 given to Sn here. And now we can add 1 to n if n ends with keep trilling 9. So the digit sum changes as and this is because the trilling 9 becomes 0, reducing the sum by 9 per 9, and the digit before trilling 9 increases by 1, adding 1 to the sum. So we just put the number in it. And suppose that this means n ends with the 4 trillionth 9. So the digit sum change fits the rules. And so the answer is we know for any n is cube, it has a fixed pattern. When the number is 0, and for number 2, number 2 here is also 2. Right, so all of them almost they're the same, and with the number is 5. This it is for all the n, and we can simplify the sum. So we need that be above the property. And we can simplify it. So and we have 2. If that is odd. And it is 4 when k is even. And we know that it is even. So the remainder is 4. Okay, for that, the last digit of n is 4 from the 44. So we know and n for when the is 5. And then we are talking about the 9 calculation, the sum of the digits from 1 to 44. That is here. And for also when total we have this, we use it into 9. And we use the Chinese remainder theorem to find the smallest x that is satisfying x here. So the solution is 9. Now we know this number is even, so when it minus 1 is odd, so it is not divisible by 2. And when we are talking about 2 now, and it is not divisible by 3. And when we talk about for the 5, we have and it is not divisible by 5. When we talk about 7, here, and the answer so that is not divisible by any prime less than 10. So we choose numbers. We can talk about the different results for n, like for n equals 1. We have here. But since 7 here, and also for n equals to 2, n equals 3, and n equals 4, and then we can get the difference xk follow. So we make the step directly for n equals to 4. And we have different xk, like as follow. And then we have to make the pattern repeats every 3 index, but with x3m here for and then to make the sum calculation, to substitute into the formula before, we have So the answer is 6. Choose A. First make the first step here. And the second one here, that equals to n plus 2 multiply n plus 1 and here, and substitute into the equations that we have a new formula. We have this, and divide both sides by n here, but it is not equals to 0. Then factor and so for n, then factor out n plus 1. And factor here. We have n plus 1 equals to 20, and n is here. And the problem that needs us to find what is the sum of the digits of n. So for n is 19, the sum of the digits is 1 plus 9 equals to 10. So the answer is 10. For this part, first we also use the factorial definitions to make different part be clearly. Here, and substitute into the equations before. We have a new one. And factor out this. This is on the left hand. And divide by n with the original one. And classify this square. It is a perfect square. Let's see. Yes, this one. It is a perfect square. So we choose the D. First, let's define sum and product. Let's let S and the original formula be here. So the sum of the first n positive and Pn equals to this. Then we simplify the divisibility condition. Okay, or here we can write another one. Because n is odd, so that is when n is bigger than 4. And we all know that n plus 1 is prime because n is even, and then n plus 1 is a prime greater than n over 2. By Wilson's theorem that we know, p minus here, that is for the prime p. Here we got this. If n plus 1 is prime and n plus 1 is bigger than 2, then the as when n plus 1 is prime, because that is not divided into the n. And let's find the largest 3-digit n. The largest 3-digit n where n plus 1 is prime. So check the primes just above 999. So the largest prime when p is smaller than 1000 is here. So I'll verify it when n plus 1 equals 997, that is prime. So we used the formula before. And we got this. since 997 is prime and it is bigger than 498, so it is not divided by it, and the answer is just 996.